This is a fairly standard C3 section B question involving some differentiation and integration. In the first part, all we have to do is to verify that the x-coordinate of P is 3. So if we take a look at the information we're given, we've got a curve with its equation, y equals x over the square root of x minus 2. We've got the lines y equals x, which is labelled here, and we've got x equals 11. So that's a line parallel to the y-axis going through 11 on the x-axis. We're told that the curve meets the lines at P and Q respectively, so P is where the curve meets y equals x, and Q is where the curve meets the line x equals 11. So verifying the x-coordinate of P, well, if it's on the line y equals x, we'd expect the x and y coordinates to be the same. So if the x-coordinate is 3, the y-coordinate ought to be 3. So we know the point 33 lies on y equals x. All we have to really do is show that the point 33 also lies on this curve. So if we substitute in x equals 3, we've got y is 3 over the square root of 3 minus 2, which is 3 over the square root of 1, which is 3. Now this square root sign, it's worth remembering, the square root sign means the positive root of. So that's the positive root of 1, which is 1, and 3 divided by 1 is 3. We haven't done y squared equals something and taken a square root to get y equals, which would lead us to a plus or minus. We're just using the definition we were given of y, which involves the square root, so that's got to mean the positive square root. So it's worth also making clear what we found then. So P, the point 33, lies on both the curve and the line y equals x. Part 2 is a show that question, so we'll need to ensure that we show plenty of working. We're going to differentiate to find dy dx and end up with this expression. We'll then make sure we keep going with the question. There are 7 marks and we do need to do a bit more. We'll be finding the gradient of the curve at P and using that to show the curve is not symmetrical about y equals x. It might be worth thinking about what this means. If the curve was symmetrical about y equals x, we ought to know what the gradient at P would be. We'll be coming back to that in a moment. So to find dy dx, personally I'd choose the quotient rule, but you could equally do the product rule if you used the denominator with a negative power rather than writing the whole thing as a fraction. So when writing down the quotient rule, I like to write down what u and v are, and then underneath each the derivative of u and the derivative of v with respect to x. So then I'm ready to start putting values into the quotient rule, and I actually remember this as bottom d top minus top d bottom all over bottom squared. What I mean by that, bottom d top, the bottom is the v, d top is the derivative of u. So it's going to be this part multiplied by this, so that's just x minus 2 to the half, which I've written here as root x minus 2, minus top d bottom, so top is the u, which is x, d bottom is the derivative of the thing that was in the bottom of the fraction, so that's a half x minus 2 to the minus a half. That's been done using the chain rule, so we do a half multiplied by the thing in the brackets to the power of 1 less than the original power, and then we multiply that by the derivative of the thing in the brackets, which is in this case 1, so we don't actually see any extra term multiplied there. The denominator then is the bottom squared bit, which is just the square root of x minus 2 squared, which just gives us x minus 2. And you'll notice that actually in this part I used a version with surds rather than with the negative indices here. You can use whichever way you prefer. Now here we've got a fraction that looks kind of like it might become this one, but we need to do a bit of tidying up. In general, if you've got something like this, I think of this as being a triple-decker fraction, then look at what the unwanted denominator is and multiply by that thing over itself. In this case, what I mean is to multiply the whole of the numerator by 2 root x minus 2 and the whole of the denominator by 2 root x minus 2. So what happens here? Root x minus 2 multiplied by 2 lots of root x minus 2 is 2x minus 2. And then the x over 2 root x minus 2 multiplied by this, that's going to cancel out to give us just an x. And then the denominator, we've got x minus 2, which you could think is x minus 2 to the power of 1, multiplied by x minus 2 to the power of a half. So if we add the powers, that's x minus 2 to the power of 3 over 2. And don't forget we've got this 2 here as well. And then if we multiply out the brackets there, we've got 2x minus 4, and then 2x minus x will leave us with x. So we've got x minus 4 in the numerator, and 2 brackets x minus 2 to 3 over 2, which is what we were required to get. So then we needed to find the gradient of the curve at P. Remember, this is the point when x is 3. So even if we couldn't do the previous parts of the question, we'd be able to substitute 3 into this given expression for the gradient. So don't think all is lost. Even if you couldn't do other parts of the question, you can still access the second part of a question, and even the second part of the second part, as in this case. So if we put in to dy dx, the value of x is 3, then we've got 3 minus 4 over 2 lots of 3 minus 2 to the power of 3 over 2, which gives us minus a half. Now, looking at this diagram, it looks like if this was going to be reflected in y equals x, the gradient at this point, well, this line here, which is a tangent to the curve at that point, that would be perpendicular to y equals x. So it would need a gradient of minus 1. However, we've got a gradient of minus a half. So we can state something that if it was symmetrical about y equals x, the gradient at P would have been minus 1, but in this case it's not symmetrical about y equals x, because we have a gradient of minus a half. In part 3, we're going to use a substitution, u equals x minus 2, to show that this integral equals 25 1/3. Now again, we've got show that, so we'll need to show plenty of working. And indeed, it's a 9-mark question, so there is going to be a lot of showing to do. But it is actually quite a straightforward integral here. There's also this extra part, which is going to be worth a mark or two, finding the area of the region bounded by the curve and the lines y equals x and x equals 11. So we'll come on to that second part in a moment. So first of all, this integration. We've got a substitution, u equals x minus 2. Whenever we've got a substitution, we need to differentiate the thing that we're substituting. So in this case, we've got u in terms of x, we differentiate u with respect to x, and in this case du dx is 1. Then we kind of rearrange. Now that's not really du divided by dx, but for our purposes we can treat it as if it was. So in this case, multiplying up, in inverted commas, we get du equals dx. So when we substitute, we can swap this dx for a du. So that bit's quite straightforward. Now, we've also got in our expression, as well as this x minus 2, which we can swap for u, we've got an x in the numerator. So we need to get x in terms of u. To do that, we can just rearrange our substitution. So if u is x minus 2, by adding 2 to both sides, we get x is u plus 2. So we're nearly there, but there's one more thing we have to remember to do, and this is to look at the limits. This is an integral in terms of x between x values of 3 and 11. We're going to turn it into an integral in terms of u, so we need to know what the u values of our limits are, not the x values. This is very straightforward to do, again just using the substitution. So our limits, we had that x was 3, and when x is 3, if we just substitute 3 in here, we get u is 3 minus 2, so u is 1. And likewise, when we're using the limit that x is 11, then we get that u is 11 minus 2, which is 9. So now we're ready to carefully substitute everything. So our new integral has the new limits from 1 to 9, which are the u values, instead of 3 to 11, which were x values. We've got the numerator, which is u plus 2. So this is our x. So the x has become u plus 2. Then we've got the denominator, which was root x minus 2. and x minus 2 is u, so that's root u. And then we've got the dx, which simply becomes du. So we might want to tidy this up a bit to make it easier to integrate. So first of all, splitting it up into u over root u plus 2 over root u, keeping the du there. It's very bad practice to miss off the d something on the end of an integral. Whenever you've got an integral sign, you should say what you're integrating with respect to. This is much more important the more different variables that could be involved. Du is not the same as dx. Show that you know the difference. So then u divided by root u is u to the power of a half. You could think of that as u to the 1 times u to the minus a half and add the powers, whichever way you prefer to think of it. 2 over root u, I'm going to write as 2u to the minus a half, and again remember to write the du. As a general rule, when you're substituting numbers in and working with algebra, it can be easier to deal with the surds, but whenever you're doing the calculus, it's pretty much always easier to rewrite things using negative or fractional powers rather than surds and reciprocals. So, to integrate, we're just going to add 1 to the power, divide by the new power. So we've got u to the half add 1 is u to 3 over 2, and then dividing by 3 over 2 is like multiplying by 2 over 3. Dividing by a fraction is the same as multiplying by its reciprocal. Same sort of thing again, we've got u to the minus a half. If we add 1, that gives us u to the half, and then dividing by a half is like multiplying by 2 over 1, so we get 4u to the half. And then crucially here, these are the u limits that we're going to substitute in. Some people make a mistake of converting back to x at this point. You don't need to. You've done all the work by doing the substitution and the limits, so we're ready just to do these limits into this simpler expression. If it was an indefinite integral, by all means, yes, we'll turn it back into an expression in terms of x. But in this case, the answer's a value. So rather than going back to the more complicated x expression, we stick with the simpler u expression. This is what we want. We've integrated with respect to u. We're now going to substitute the u values in. So we've got 2/3 times 9 to the power of 3 over 2 plus 4 root 9, and then we subtract what we get when we substitute in the 1. Now it's worth putting these brackets here, because if you don't, then you might not get that this is actually subtracting 4 here, and then you'll obviously be out by about 8. So it's very important to put the brackets in when you're subtracting. Okay, so evaluating that, use a calculator by all means. I happen not to have one to hand, so I wrote maybe an extra line of working that would be required, but for a show that question, it's always worth showing plenty of lines. You absolutely must show your integral with the new substitution and the line with the square bracket showing what you're going to substitute the numbers into, and the line showing how you substituted the values in, and then your final answer line, which in this case was given. So we end up with 25 1/3. And finally, in this question, we were asked to find the area of the region PQR bounded by the curve and the lines y equals x and x equals 11. So just take a moment to check that you can see where they're talking about. So PQR bounded by the curve, the line y equals x, and the line x equals 11. So that's the region that I've done with the blue shading here. And so to get that, we can use the previous answer. So again, even if we couldn't do the previous part of the question, we should be able to find this area. So the area from the previous part was the area beneath the curve to the x-axis from x equals 3 up to x equals 11. So this part I've shaded in purple is the 25 1/3 from the last part. Then what we've got here, we could integrate the line y equals x, but it's probably easier to just spot that this is a trapezium. So if we do half multiplied by this y coordinate plus this y coordinate multiplied by the width of the trapezium, which in this case is 11 minus 3, which is 8, and that will give us the area of that trapezium. Subtract the 25 1/3, what we're left with is the area that we're looking for. So we've got, from the formula, it's like half a plus b h, so that's 3 for the height at P, 11 for the height at R, 8 is the width of the trapezium, and that gives us a half times 14, which is 7 times 8, so we've got 56 there, and we subtract the 25 1/3 to give us 30 2/3 square units.